Welcome to the podcast where we peck away at the mysteries of artificial intelligence. I'm your host, Professor Hoot, and today we're embarking on a fascinating journey to understand the engine behind some of the most mind-boggling AI creations we've seen recently. Mr. Beaver, it's great to have you.
Thanks for having me, Professor Hoot. I'm ready to shed some light on the magic happening behind the scenes of modern AI.
All right, Mr. Beaver, let's set the stage. Our listeners are probably very familiar with all the incredible things AI has been doing lately. We've seen AI write essays, compose music, create stunning artworks from simple text descriptions, and even generate realistic videos. It's truly amazing, almost like science fiction becoming reality, but for many it still feels a bit like magic. In fact, I and you won't be sitting here if this magic didn't happen. Can you give us a high-level explanation of how these things are actually happening?
The core behind this innovation is a powerful field called Generative AI, which enables machines to create content like text, images, and more.
Generative AI? Tell us more about that.
Earlier, AI was mostly used for tasks like spotting cats in images or predicting stock prices. But generative AI is different. It's designed to create. It learns from data and then makes something new, like it's being creative, not just copying. It studies patterns and styles from tons of data, text, images, or audio, and uses that to create something new. So when AI draws a cat in a spacesuit, it's not copying, it's imagining it from scratch, pixel by pixel, based on what it has learned.
So it's not just recognizing, it's creating. That's a big shift. But what exactly are these LLMs we keep hearing about, and how do they power generative AI for text?
Large language models, or LLMs, are a powerful type of generative AI focused on language. They're behind tools like chatbots, writers, and summarizers. What makes them large is the huge amount of text they're trained on, basically most of the internet. And as models, they use complex neural networks to predict the next word in a sentence. This simple task, done at scale, helps them learn grammar, facts, reasoning, and nuance. Predicting the next word sounds simple, but it's the key in generative AI. So, what exactly is a transformer model, and why is it the backbone of today's AI revolution?
Transformers are the engine behind today's AI magic. Introduced by Google in 2017's Attention is All You Need, this neural network architecture powers the incredible abilities of LLMs. Before transformers, recurrent neural networks, or RNNs, and convolutional neural networks, or CNNs, were the dominant architectures for processing sequential data like text. They worked well for shorter sequences, but they had significant limitations, especially with very long sequences. RNNs process data word by word, struggling to remember information from the very beginning of a long sentence. This sequential processing also made them slow to train.
So, how these problems were solved that RNNs and CNNs faced, especially with long sequences? What made the solution so revolutionary?
That's where this core innovation comes in: attention mechanisms. Unlike RNNs, which process data sequentially, word by word, the transformer can process all words in a sequence simultaneously. This parallel processing, combined with their ability to intelligently weigh the importance of different words in a sequence relative to each other, made them incredibly powerful. This breakthrough radically improved performance for tasks like machine translation, text summarization, and yes, eventually, large-scale text and even image generation.
So it processes everything at once and learns word relationships. Fascinating. But what exactly is inside a transformer model? What are its key parts?
Absolutely. Let's break down the main constituents of the transformer architecture. A standard transformer typically consists of two main parts, an encoder and a decoder. Think of the encoder as the understanding part. It takes an input sequence, like a sentence in English, and processes it to create a rich numerical representation or encoding of that sequence. This encoding captures the meaning and context of each word within the sentence. The encoder itself is a stack of identical layers. 2. The decoder. The decoder, on the other hand, is the generating part. It takes the encoded representation from the encoder and uses it to generate an output sequence, for example, the translated sentence in French. The decoder also generates its output word by word, but crucially, it can pay attention to different parts of the input encoding at each step. The decoder is also a stack of identical layers. Each encoder layer and each decoder layer share some common building blocks, but with slight variations. Let's look at the core components within a single transformer layer. Within an encoder layer, you'll primarily find two sublayers. One multi-head self-attention mechanism. This is the heart of the transformer. It's what allows the model to weigh the importance of different words in the input sequence when processing a specific word. We'll dive much deeper into this in a moment. 2. Position-wise feed-forward network. This is a simple, fully connected neural network applied independently to each position, each word's representation, in the sequence. It adds nonlinearity to the model and helps it learn more complex patterns. Crucially, both of these sublayers are wrapped with residual connections and layer normalization. Let's talk about residual connections. Imagine you have a complex calculation. A residual connection means you add the input of a block directly to its output. This helps with training very deep networks by allowing gradients to flow more easily. This concept was popularized by ResNet architectures in computer vision. Now the layer normalization. This technique normalizes the activations of each layer, which helps stabilize training and allows for faster convergence.
Got it. Now, you mentioned multi-head self-attention is the heart. This sounds like the real magic. Can you explain what self-attention is and then how multi-head plays into it?
Absolutely. This is where the attention is all you need really comes into play. Let's start with self-attention. Imagine you have the sentence, "The animal didn't cross the street because it was too tired." When the transformer processes the word it needs to understand what it refers to. Does it refer to the animal or the street? Self-attention allows the model to look at all other words in the input sequence and decide how much attention to pay to each of them when encoding it. It does this by creating 3 learned vectors for each word in the input. Query. Think of this as the question or what we are looking for. Key. This is like the index or what other words are offering. Value. This is the actual information or content of the word. The process works like this. For each word, we calculate a score by taking the dot product of its query vector with the key vectors of all other words in the sequence, including itself. This score indicates how related each word is to the current word. These scores are then passed through a softmax function to get probabilities. These probabilities tell us how much attention to pay to each word. Finally, we multiply these attention probabilities by the value vectors of all words and sum them up. This weighted sum becomes the new representation of the word, enriched with context from all other words.
That's incredibly elegant. Now, what about multi-head? Why not just one head of attention?
Excellent question. The multi-head part is crucial for capturing different aspects of relationships between words. Imagine trying to understand a complex concept. You might look at it from different angles or perspectives. Multi-head attention does precisely that. Instead of performing self-attention once, we perform it multiple times in parallel, each time with different learned query, key, and value transformation matrices. Each of these parallel attention mechanisms is called an attention head. Each head learns to focus on different types of relationships. For instance, one head might learn to focus on syntactic relationships, e.g. subject-verb agreement, while another might focus on semantic relationships, e.g. synonyms or antonyms. The outputs from all these heads are then concatenated and linearly transformed to produce the final output of the multi-head attention layer. This enriches the representation even further by incorporating diverse contextual information.
That's brilliant. Now, you mentioned the decoder also has attention. How does the attention mechanism in the decoder differ from the encoder?
The decoder has 2 attention mechanisms. One masked multi-head self-attention. This is similar to the encoder's self-attention, but with a crucial difference. When the decoder is generating a new word, it should only be able to attend to the words it has already generated in the output sequence. It cannot cheat by looking at future words. So we mask out the future positions during the attention calculation. This ensures the autoregressive property, meaning it predicts the next word based on the previous ones. 2. Encoder-decoder attention, or cross-attention. This is where the decoder interacts with the encoder's output. For each word the decoder is generating, it performs attention over the entire encoded input sequence. This allows the decoder to focus on the relevant parts of the input when generating each output word. For example, when translating dog, it might attend to the word chien in the English input. Here, the query comes from the decoder's previous output, and the key and value come from the encoder's output. This combination is what makes the transformer so powerful for sequence-to-sequence tasks.
Speaking of sequences, how does the transformer handle the order of words? You said it processes words simultaneously, which sounds like it would lose the sense of sequence. How does it know which word comes after which?
This is where positional encoding comes in. Since the transformer processes all words in parallel, it doesn't inherently understand the order of words. If we just fed in the word embeddings, dog bites man would be treated the same as man bites dog. To address this, we add positional encodings to the input embeddings. These are numerical vectors that carry information about the absolute or relative position of each word in the sequence. The original transformer paper used sine and cosine functions of different frequencies to generate these encodings. These are added to the word embeddings before they enter the encoder and decoder stacks. This way, each word's representation is unique, containing both its semantic meaning and its positional information.
That's clever. We've talked a lot about the components and how they fit together. Now, let's get a bit more technical. Could you walk us through the actual working of the transformer, perhaps with some of the underlying mathematics?
Absolutely. Let's delve into the mechanics. The fundamental operation within the attention mechanism is the scaled dot product attention. The formula for scaled dot product attention is this. Let's break this down. QKV. These are matrices representing the query, key, and value vectors for all words in a sequence. Each row in Q, K, and V corresponds to a word's respective vector, QKT. This is the dot product between the query matrix and the transpose of the key matrix. It calculates the similarity score between each query and all keys. DK. This is the scaling factor. DK is the dimension of the key vectors. Dividing by the square root of DK helps to prevent the dot products from becoming too large, which could push the softmax function into regions where it has very small gradients, hindering learning. This is a crucial detail for stable training. Softmax. As we discussed, this converts the similarity scores into probabilities, ensuring they sum to 1. V. Finally, we multiply these attention probabilities by the value matrix. This takes a weighted sum of the values, where the weights are determined by the attention probabilities.
So, the core idea is measuring similarity, scaling it, normalizing it, and then weighting the values. And that DK factor is for stability, very important. What about the multi-head part in mathematical terms?
For multi-head attention, we essentially perform this scaled dot product attention multiple times in parallel, as we discussed. The formula for multi-head attention is YQ, WIC, with these are learned weight matrices for each head I. We project the original Q, K, and V into different subspaces for each head. This allows each head to learn different representations and focus on different aspects of the relationships. Concat head 1, 2, head the outputs from all H attention heads are concatenated joined side by side. WO. This is a final learned linear projection matrix that transforms the concatenated output back into the desired dimension for the next layer. This mathematical framework allows the transformer to learn highly sophisticated patterns and dependencies within sequences, regardless of their length.
This is truly a marvel of engineering and mathematics. Now, let's fast forward to today. Transformers were introduced in 2017. How have modern-day large language models, or LLMs, like ChatGPT, DALL-E, and others, utilize these architectures to generate text, images, and even videos? And how do they manage to keep context and save history in their interactions?
This is where the true impact of transformers becomes evident. They are the foundational architecture for nearly all state-of-the-art generative AI models today. Let's look at how LLMs utilize them for text generation. 1. Scaling up. The core idea is to scale up the transformer architecture to an enormous degree. We're talking about models with billions, even trillions of parameters. These models are typically decoder-only transformers. This means they only have the generative part of the transformer, taking a given text as input and predicting the next word repeatedly to generate long sequences. 2. Pre-training and fine-tuning. LLMs are first pre-trained on massive datasets of text from the internet, books, articles, websites, conversations. During pre-training, they learn to predict the next word in a sentence, a task called causal language modeling. This allows them to learn grammar, syntax, factual knowledge, and even common sense. After this massive pre-training, they can be fine-tuned on smaller, more specific datasets for particular tasks, like translation, summarization, or answering questions. 3. Context and history. This is a crucial aspect of conversational AI. LLMs keep context primarily through their attention mechanism. When you interact with an LLM, your entire conversation history, up to a certain length, is fed into the model as part of the input. The transformer's self-attention mechanism then allows it to weigh the importance of past turns in the conversation when generating its current response. The model essentially remembers the relevant parts of the dialogue through its attention weights. There's a limit to how much history they can retain due to the context window size, which is a fixed number of tokens. Beyond that, older parts of the conversation are usually truncated.
What about generating images and videos? How do transformers handle non-textual data?
For image generation, models like DALL-E and Stable Diffusion also rely heavily on transformers, but with a clever twist. Tokenizing images. Images are first broken down into smaller, discrete units, similar to how words are tokens in text. These can be image patches or visual tokens, learned by a separate component called a tokenizer. Latent space. Often, these models work in a latent space, a compressed representation of the image data. A transformer then operates on these visual tokens in the latent space, using its attention mechanism to understand how different parts of an image relate to each other. Diffusion models. Many modern image generation models combine transformers with diffusion models. The transformer helps guide the diffusion process, which gradually refines random noise into a coherent image based on a text prompt. The transformer effectively learns the relationship between the text prompt and the visual features. For video generation, the challenge is even greater because it adds the dimension of time. Let's look at, first, the temporal attention. Video transformers extend the concept of attention to include not just spatial relationships within a frame, but also temporal relationships between frames. They can attend to different parts of the video sequence over time to understand motion and events. And then combining architectures. Often, these models combine transformer blocks with other architectures, like 3D convolutions, to efficiently process the spatial temporal data. The transformer's attention allows them to learn long-range dependencies across many frames, which is crucial for generating coherent and realistic video.
So, they essentially tokenize images and videos, and then the transformer's attention works its magic on these visual tokens, often in conjunction with other powerful models. It's truly incredible how versatile this architecture is. Now, let's talk about the future. What are the current and futuristic applications of transformers? And what are some of their shortcomings that need improvement?
The applications are already vast and continue to expand at an astonishing pace. Let's look into some. 1. Advanced Natural Language Processing, NLP, beyond simple text generation. We're seeing transformers power highly sophisticated conversational AI, personalized content creation, complex legal document analysis, real-time language translation with nuances, and even creative writing assistants that can generate poetry or scripts. 2. Multimodal AI. This is a huge area. Transformers are enabling models that can seamlessly understand and generate across different modalities: text-to-image, text-to-video, image-to-text captioning, and even text to 3D models for virtual reality and gaming. Imagine designing a virtual world by just describing it in text. 3. Drug discovery and material science. Transformers are being used to analyze complex molecular structures and protein sequences, accelerating drug discovery by predicting protein folding or identifying potential drug candidates. In material science, they can predict properties of new materials based on their atomic arrangements. 4. Robotics and autonomous systems. Transformers can help robots understand natural language commands, process sensor data from their environment, and even learn complex manipulation tasks by observing human demonstrations. This could lead to more adaptable and intelligent robots. 5. Scientific discovery. From analyzing astronomical data to understanding complex biological systems, transformers are proving invaluable in extracting insights from massive datasets in various scientific fields.
From creative arts to scientific breakthroughs. But, like all powerful technologies, I assume transformers have their limitations. What are some of the shortcomings that researchers are actively working to improve?
Transformers are powerful, but they come with challenges. First, their attention mechanism scales quadratically, making them extremely memory and compute-intensive for long sequences. They can also generate hallucinations, confidently producing false information because they lack real-world understanding. Another issue is explainability. Their internal logic is complex and often a black box, especially in critical domains. They may also reflect or amplify biases present in the training data, leading to unfair or unethical outputs. Finally, training and running these large models consumes enormous energy, contributing to a growing environmental footprint.
Those are indeed significant challenges. It sounds like there's still a lot of fascinating research to be done. This has been an incredibly insightful conversation with our AI expert. You've taken us from the captivating outputs of AI to the fundamental architecture that makes it all possible. And I think this understanding gives our listeners a greater appreciation for both the power and the limitations of these technologies. And this brings us to a very important point for our listeners. As AI-generated content becomes more sophisticated and ubiquitous, it's increasingly important for us to be discerning consumers of information. Whether it's an essay, image, or news article, look for subtle flaws, repetition, or missing human nuance. It's not fear, it's AI-age media literacy. Tools can help, but your critical eye is the best detector. Stay curious. Stay aware.
An excellent call to action, Professor Hoot. Critical thinking skills are more vital than ever in this new landscape.
Indeed. Thank you again, Mr. Beaver, for this illuminating discussion. And that wraps up our episode. We hope you've gained a clearer understanding of generative AI, large language models, and the pivotal transformer architecture. Join us next time as we continue to explore the cutting edge of artificial intelligence.